Good evening. My name is Gerard Beagle, and I'm president of Shannon & Wilson. On behalf of Shannon & Wilson and the University of Washington Civil and Environmental Engineering Department, I'd like to welcome all of you to the 2019 Standley D. Wilson Memorial Lecture. It's great to see so many of our friends in attendance. This year we celebrate our 65th anniversary since the founding of our firm by Stan Wilson and Bill Shannon here in Seattle. Mr. Shannon was involved in many high-profile projects during his time at Shannon & Wilson. He became the founding president of the Associated Soil and Foundation Engineers, now known as ASFE-GBA, as well as a founding member of Terra Insurance, a group formed to provide professional liability insurance for the engineering community. We appreciate the contributions that Mr. Shannon made to our profession. Our other co-founder, Stan Wilson, has often been characterized as the idea man. He was technically gifted and was respected for his extensive knowledge of earth and rock-filled dams and their instrumentation. He developed instruments to measure displacements and distortions in soil and rock, many of which are still widely used today. Stan served as a consultant on large projects all over the world. On one of his consulting trips, he contracted malaria, and in 1985, his career was sadly cut short by an untimely death from complications of the illness. To honor Stan's legacy, our firm established the Wilson Lecture in 1989 to foster and maintain the spirit of thoughtful and practical engineering solutions. For this year's lecture, it's an honor and a privilege to have Dr. Raymond Seed, Professor Emeritus at the University of California at Berkeley. Dr. Seed was educated at Berkeley, receiving his BS degree in civil engineering in 1980, his MS and PhD degrees in geotechnical engineering in 1981 and 1983, respectively. Professor Seed served as a professor of civil engineering at Stanford University for 4 years before spending 31 years at UC Berkeley, where he continues to serve as Professor Emeritus. Since 1982, Professor Seed has served as a geotechnical consultant to numerous domestic and foreign engineering firms and government and civil agencies on problems spanning a number of areas, including geotechnical earthquake engineering, static and seismic stability evaluation, design of dams and embankments, analysis of soil structure interaction, and many others. The author of more than 200 professional research publications, Professor Seed's research activities also span a wide range of subject areas. His research has had a significant impact on geotechnical practice in a number of areas, including seismic stability and performance evaluation for dams and embankments, analysis of soil liquefaction potential and post-liquefaction behavior, analysis of reinforced soil systems and deep-braced excavations, and many others. He has led and or participated in forensic studies of several U.S. and international major earthquakes, multiple slope and dam failures, a tsunami, and the Kettleman Hills waste repository failure. He also led the NSF-sponsored independent investigation of the performance of the New Orleans levee systems following Hurricane Katrina. Among the professional honors accorded to him, he's received numerous awards, including the ASCE Thomas A. Middlebrooks Award, both in 1987 and 2006, the ASCE Edmund Friedman Young Engineer Award for Professional Achievement, the ASCE Arthur Casagrande Award, the ASCE Huber Research Prize, and the Presidential Young Investigator Award from the National Science Foundation. Without further delay, please welcome Dr. Raymond Seed.
Thank you very much, and it's a pleasure and an honor to be here. Stan Wilson is an opportunity not to be missed by anybody who understands the history and the evolution of soil mechanics. This is a big deal for me, and I want you to know I'm humbled and I'm very nervous. It doesn't happen very often. We're going to talk today, and it's a good news talk. This is one of my favorites. Most of my life I've spent making your lives harder because we keep finding reasons why we're not doing it right and we're unconservative. This is one where we're actually doing it right and we are over-conservative, so residual strengths are going to go up. There's a small caveat to that. Liquefaction triggering is going to get worse, and it's going to get worse in places like this, where you're in the heart of the subduction world. But having said that, residual strength is going to start to be your friend, and it may get you out of the woods on more than a few occasions. The title of my talk is Residual Strength, 3 Decades to Consensus. That's about where we are. Post-liquefaction residual strength has been a fractious issue for about the last 35 years, and a bit more if you're a real historian. But in the last 5 or 6 years, we seem to have sort of pulled it together, gotten our hands around it, and we're able to cross-triangulate between a number of research efforts and perhaps wrap it up and lasso it and maybe even brand it, beginning to give you what I hope are reliable, useful engineering post-liquefaction strengths. There will in this talk be 2 pairs of heroes besides our own research team, and especially Joe Weber, whose doctoral research this was at UC Berkeley. Joe did one of the longest modern PhDs in the Berkeley geotechnical program because of the volume of work involved. His wife still hasn't forgiven me. The 2 pairs of heroes will be Stark and Olsen, and Kramer and Wang, and their names will come up a number of times. If they hadn't done what they did, this would not be a consensus. This would be another arrow off into the dark. We're grateful to our advisory and consulting board on this project. There were a large number of people involved in the actual work, and there were some very good people involved in review, consultation, and advising. We're looking at step 2 of what is sort of a 5-ring process for liquefaction engineering. The second step, after you decide if you're going to have a liquefaction problem, is to assess the post-liquefaction stability and strength, and that's where we'll spend our afternoon. We're going to use the Lower San Fernando Dam as essentially a central case history. It'll pass through the talk repeatedly, but it's one of 51 cases that we evaluated and one of 31 cases that we back analyzed. As many of you know, it suffered an upstream catastrophic flow failure during the 1971 San Fernando earthquake. This is a photograph of the dam as it appeared from the air. This photograph was taken by Dr. Lloyd Clough from a helicopter. He was that year the chair of the State Seismic Safety Commission, so he got the first helicopter. When he got to the Lower San Fernando Dam, he realized that the crest was missing. Ordinarily, the crest road goes all the way across, but it's not just the crest. In addition to missing the crest, oops, I have a small mouse, there we are. The outlet tower here is supposed to have a partner right here. It's also missing. It was carried out by the slide. There were about 5 to 7 feet of crumbling soil left at the time this photograph was taken, and crumbling is an important word. What we call that now is transverse cracking. And so there wasn't a whole lot of freeboard keeping that reservoir intact. Dr. Clough circled until he ran out of gas and had to land because he was pretty sure he was going to see this fail. 80,000 people downstream were evacuated for the next week and a half till it was safely lowered, and we had a pivotal case history which was foundational to our modern seismic dam safety programs, which are still ongoing today. After the failure, an extensive field investigation was undertaken. My father was involved in a lot of that, so this is sort of a family thing for us. What they did was they trenched through the dam, figure at the bottom, and they mapped and labeled, actually numbered, the intact pieces. And then my father, on our family's dining table, with my mother ragging on him, reassembled the puzzle up at the top, and they realized that the dark zone, that wedge at the bottom of the hydraulic fill, was the material that had liquefied. It was a hydraulic fill dam with sandy shells on the upstream and downstream side and what's called the puddled central clay core in the middle. That piece had liquefied, and the embankment had slid upstream, borne aloft atop the liquefied material. This is one of the key back analysis case histories for post-liquefaction strength. Makes a good example, and now that you're familiar with it, we'll just use it all day. This dam was back analyzed by lots of people for different reasons. It's usually back analyzed for purposes of triggering or seismic deformation prediction, but it was also back analyzed in a joint effort between UC Berkeley, UC Stanford, RPI, the Corps of Engineers, and Poulos and Castro of GEI consultants as an evaluation of their post-liquefaction residual strength or steady state method. These are the results of that testing program, consensus testing program, These are the sandy and silty sandy materials at the base of the upstream shell. And what you do in this method is you have a laboratory test result. That laboratory test result is what you have in the laboratory after you've taken the sample from the field, brought it home, extruded it, trimmed, and consolidated it back into shape, and they're ready to test it. The field condition is estimated to have been back here. It's a big stretch to how you get back there. There's two pieces to this. One is you have to first of all do about 30 tests on disturbed materials formed at different densities and establish a steady state line for the disturbed materials. And then you assume you have a parallel path back to the field void ratio. The void ratio in the field is established by putting a geologist or an engineer in the bottom of a deep hole if you have a big dam, and they hand carve a sample while slowly advancing a cylindrical tube around it. They put a metal plate across the bottom, pick it up, and they carry it home themselves. They don't get in a truck. They ride in a car with good springs. They don't ride any airplanes, and they get it back to the lab. And they know the cutting diameter, they know the push length, they know where it was cut off, and they remeasure the sample dimensions back in the lab, and they know exactly how much volume has been changed or lost, usually by densification, on the way home to the lab. And you make a correction from the tested condition back to the assumed field condition, and in this case you make an extra correction for earthquake consolidation, because this is a post-earthquake failure. First thing you'll notice is the correction is not trivial. This is a logarithmic scale. Second thing you notice is you make the correction parallel to the steady state line for disturbed samples. There's no particularly good reason to think they would behave the same. There are some massive assumptions in this. The conclusion at the end of this program, which was a consensus program, was this is not a procedure that we want to be using in all likelihood. It is an approach taken with tailings dams still, but it's not used much on regular dams because of this kind of research effort. But it was an early program, and it motivated good thought about post-liquefaction residual strength, and it sort of set the ball in motion. My father was so upset by this that he developed this relationship, and this is a piece of research done by the Bureau of Reclamation, who joined on shortly after. These are values developed from that previous process by Poulos and Castro's GEI lab team. And these are materials that are recommended as SR values for different elements in the dams or foundations of 6 projects under work by the Bureau of Reclamation. 5 of them are listed. And this is a zone reflecting back analysis and plotting of residual strength from calculation of stability by my father. And what it found was that only a few of these fall within it. Most of them fall above it. And the ones up here are sufficiently far above it that you actually would have to be up on the next floor of the building to plot those numbers, so expanding the page wouldn't help you a whole lot. And that was sort of the end for a while of the Poulos and Castro method, but it was also sort of the inception of using back analyses in an empirical method, not unlike the empirical methods used for liquefaction triggering, also based on case histories. Then we have to talk about what makes post-liquefaction residual strength such a challenge. This is the hydraulic fill of the upstream shell that liquefied and did what it did in the San Fernando earthquake. And what you see is what you usually see with liquefiable soils. Liquefiable soils can be placed by engineers as hydraulic fill. They can be placed as rolled fills. They can occur as alluvium. They can occur as aeolian deposits. The nature of liquefiable soils is they occur in layers. And layers are bad. Layers are bad for post-liquefaction residual strength. What you can see here in the shell materials of the dam is layers caused by having to periodically halt the placement of the hydraulic fill and move the pipes, raise new dikes, refill the pond, and start again. But you'll also see, if you go in closer, that the white zones there, which are sandier, have darker lines in them, which is siltier and silty clayier material. And if you look in close in those smaller bands of lighter material between the smaller layers, you find even smaller layers. And so when I do this in class, I recite the poem I learned when I was about 5. Little fleas have smaller fleas upon their backs to bite 'em. And the smaller fleas have smaller fleas, and so ad infinitum. Layering recurs at all scales, and each of those layers has two kinds of material, a coarser fraction, which is more prone to cyclic pore pressure generation, and a finer fraction, which impedes drainage. And so you've got encapsulated layers. And within those layers, and you can take a big one that you can see, or you can look at a smaller one, when you liquefy the material, you get overall no volume change because it's undrained for a short while, certainly for the seconds of an earthquake. But while you have no volume change, you have a void redistribution. Solid particles settle, and to maintain constant volume, fluid moves upwards. A very small change in density causes a large decrease in post-liquefaction residual or steady-state strength. And so these things fail along the tops of layers. And they fail at a condition that did not exist before the earthquake. It's a new condition that arrived during the earthquake that controls your fate. There's no sample that you can take that would tell you what that condition will be, and there's no geologist in the world that can tell you at what scale that redistribution will occur. That is the problem. This does not violate critical state soil mechanics. It embodies it. The layer that actually fails at critical state. But you can't capture that in most constitutive models because it's a new material condition that evolved during the earthquake. It wasn't there before you started. So none of the testing you did characterized it properly. And that's why we use empirical methods, usually penetration test based, and back analyses of actual case histories where all that void redistribution occurs at the various scales that it wants to, and we get a statistical sampling of that. To do that, you need to have enough case histories to make it viable and valid. But that is why there are fierce debates between academicians who absolutely love critical state soil mechanics and pragmatists who say they're nuts. I have one leg in each camp. I do think they're nuts, but I love critical state soil mechanics. There is no conflict as far as I'm concerned. This is just nature taking advantage of her ability to defeat us by creating a more serious failure condition than our nice models would like to envision. It is my view that nature views us as fleas, and perhaps she's trying to eradicate us. So my father, in the last year and a half of his life, back-analyzed a small number of failure case histories and developed this correlation. This was in 1986, and he published it. It was his last paper in the ASCE Geotechnical Journal, and then he died. And when the paper appeared, I realized he'd made an error. Two of these dots are based on post-failure analysis of the existing geometry, not a deformed condition, and that would overestimate strength, so this relationship would likely therefore be unconservative. So his last PhD student, Dr. Les Harder, and I reworked the case histories. We also dug out 5 more and published a second correlation. Because we were simply fixing his error, we didn't publish it in the ASCE Geotechnical Journal. It was published in his memorial symposium proceedings. But unfortunately, it took on a life of its own and became the Seed-Harder method. Some of you will have used it. These are the 2 cases that had to be moved, and there's 5 more dots than there were in the previous figure. And that's kind of how it began. As soon as we did that, figure on the left, Professor Stark and Professor Mesri at Illinois looked at this and said, this is an undrained failure. And for those of you who know Professor Mesri, he's all about SU over P because he's a clay guy. He's a really good clay guy. He can be very frustrating, but he's really good at clay. So Stark and Olsen reprocessed the data sets, and they posed it not as SU, but SU over P versus flow count N160. Actually, N160 finds corrected CS. And suddenly, there were 2 schools of thought. That was never really a debate. The answer was always going to lie somewhere in the middle. Both N160 CS and initial vertical effective stress were going to affect the outcome, and there was a need to develop correlations that would do both. That didn't happen for a while. A hybrid position was postulated first by Bozier and Dobry. Good old Ricardo kept his finger on the pulse and saw an opportunity here, and he published a relationship. It was actually clever, but it was also absolutely unintelligible, and I bet none of you noticed it. It was actually a pretty clever relationship. We put one out in 2003. Steve Kramer and Dr. Wang put one out in 2008 and published an ASE paper in 2015. Dave Gillette of the Bureau of Reclamation actually has two relationships. He took other people's data and did his own regressions, and so it went. And these regressions shown here are all hybrid, where they use both SU or SU over P as a function of N160CS. But what they're really doing is they're predicting post-liquefaction strength SR as a function of N160CS measuring the density and sigma V prime measuring the initial starting vertical effective stresses. And that will be our approach tonight. When we began our project, a lot of work had been done. Many people had done these analyses. There were a lot of cases assembled. 51 of them looked vaguely tenable, and so we evaluated them in detail. Out of those, we picked 31 to analyze. 20 of them fell by the wayside. Some of the ones that went away were old favorites. One of them was the Nevada apartment buildings. The building that fell over is one of my favorite slides when we start our graduate earthquake course. The owner at this site, which is in Nevada, these are the apartments in Nevada, was told by his geotechnical engineer that there was something wrong with the site. Liqua something. So he correctly instructed his structural engineer to build these apartment buildings in a more sturdy fashion. And I should tell you that the structural engineer was entirely successful in that, and these buildings are undamaged after the earthquake. The aluminum sliding frame windows open and close, the interior doors open and close, and there are no significant cracks in these buildings. They are uninhabitable, tilting as they are, and there was no way to level them, so they had to be disassembled with jackhammers and welding torches. But the structural engineer was entirely successful in his assigned task of making them sturdier. And this is one of my favorite examples of liquefaction engineering for beginners, because you do not solve liquefaction in the superstructure, you solve it in the foundation. This case history goes away because as a residual strength for back analysis, we have no idea what the inertial forces were as these buildings were shaking back and forth. We can't even begin to estimate them. That's a very complicated problem of the tipping and the rocking. So this one's off the list. Another favorite was Calaveras Dam, which suffered a catastrophic flow slide during construction. Unfortunately, I worked on Calaveras Dam, and what I learned was two large zones of the failure were in cohesive soils, which were an ugly mix of silty, clayey, sandy gravel with cobbles. And we really can't characterize those materials properly for our purposes, and they may have been cohesive dominated. And so this one sadly falls off the list, although we do analyze it in this current study for the mechanics of flow failures, because it did have a flow failure. We just can't lump it in with the other more cohesionless materials. And so it goes. When we're all done, we pared it down to 31 cases, and then we dug in. In a minute, I'm going to suggest that there are probably 5 useful ways to do back analysis of failure case histories for purposes of evaluating post-liquefaction residual strength. But I want to begin by pointing out that there are 4 ways not to do it, and they've been common. These are 4 bad ways. One is to analyze the pre-failure geometry and assume a factor of safety of 1. That's been done. If in fact the factor of safety was 1 and the earthquake came and it liquefied, it would move how far? That would be not at all, or an inch, and that's not what happened, so that's the wrong answer. Second way to do it is to back analyze the post-failure residual geometry with a factor of safety of 1. That's incorrect. It is not barely stable in its run-out condition. If a Sanfran dam has a flow failure and it slides 143 feet back into the reservoir, there was an enormous amount of momentum that had to be brought back to rest. And to put momentum back into inertia, you have to apply the brakes. You have to apply a strength significantly higher than what will then hold it in place under static conditions. So method number 2 would massively underestimate S sub R. 3 is to analyze an incorrect failure mechanism. This one's been very popular. I won't point any names out. And number 4 is to adopt values from other researchers without ascertaining their reliability. A lot of people have back-analyzed case histories and published their answers without showing their cross-sections or their work. In graduate school at Cal, that gets you an F. Got to show your work. So, there are 5 potentially useful ways to back-analyze case histories, and we're going to go through all 5 of them. We're going to do 3 in detail because the ones shown with an arrow are the 3 that we used as our principal tools. We'll look also at numbers 2 and 4. Number 2 was done by Kramer and Wang, and number 4 was done by Stark and Olsen. We could have done that too, but they documented their work very nicely, and we liked their answers. We didn't agree with all of them, but we liked them. We'll begin with method 1, incremental inertial analysis. We're starting there because it's fun. It's also probably the best way of doing this, but it's fun, and people enjoy this. We call this the Pixar animation. This is, again, the San Fernando Dam, Lower San Fernando, as it appeared in the bottom figure after the earthquake and top figure before the earthquake. We know both of those geometries in good detail. The question is, how do you transition from one to the other, and can you use it analytically? And the answer is yes, you can. So you want to watch the middle of this figure, then we'll look at the top, and then we'll look at the bottom. But for now, watch the middle one, because that's our Pixar animation. This is Joe Weber's work. What you have there is the cross-section of the dam reassembled as a jigsaw puzzle, and I'm going to begin to push a button, and the dam will begin to move back into the reservoir as it liquefies and flows. We'll do it a couple of times, so you haven't got to really watch closely because you'll get several chances of this. We'll also do it backwards, which is equally fun. That's how we think it moved. We've tried a lot of other combinations, but that's the only combination that lets us put all the pieces where they have to be at the end. So I'll back it up again and do it again. Ready? Now that answers a number of important questions which have long been controversial, one of which was, there are a series of slices here which come apart and end up disaggregated downstream. The question is, did they come off one by one, or did they begin to move together and then separate as they traveled? And the answer is they came off together and separated as they travel. You can't ram the back 2 ones under the other ones far enough unless they began moving together. So that question gets answered. Okay, the figure at the top is the same figure, except this time instead of doing it in disaggregated pieces, we're going to track the overall failure mass and the dot. The dot is the centroid of the failure mass, and it will move as the mass travels. And we're going to do calculations of the mass, and we're going to plot what happens with the centroid in the bottom figure. We'll track the acceleration of the centroid, the velocity, and the displacement of the centroid from the beginning of the event until the end of the event. Velocity, you'll notice in the middle, begins at 0. Acceleration also begins at 0. Displacement also begins at 0, but acceleration will begin at a downslope significant acceleration. It'll come back to 0 and travel in the other direction. Velocity will go up and come down again, and of course displacements will accumulate. And again, we'll do it twice. Velocity reaches a peak and comes back down, and displacement has accumulated. Acceleration became negative at the end. This did my heart a world of good. I struggled through the first physics class at Cal. It's taught not in engineering, it's taught in physics, and they don't make it easy for us. They take no prisoners. But I learned that you can integrate acceleration and get velocity, and you can integrate velocity and get displacement. And by golly, it works. It's also how we do the back analyses of what we call the class 1 case histories, of which there are 11. And physics is preserved. All the shear surfaces have assigned shear strengths. The frictional materials, we know more or less how they behave. The clay core, we know more or less how it behaves at small strains and at larger strains. And so the unknown remaining variable is the undrained strength of the liquefied material. And so we solve this back and forth until when we're all done, the final geometry is also the geometry observed. And then we have 1 point for a plot of data of post-liquefaction strength versus N160. Okay, now we're going to do the second method This one's important for understanding at a conceptual level, and it serves as more or less the framework of understanding. We call this one before and after. What you do here is you look at the cross-section as it existed just before the earthquake, just before the failure, and as it existed at the end when everything had stopped moving. The top figure is before, the bottom one is after. If you looked at the top figure and asked yourself, what would the strength have to be in order to just barely yield that and have it start to move? The answer would be 1,281 pounds per square foot, as close as we can figure it. In the bottom figure, the residual geometry, you ask yourself, what would the strength have to be to just barely hold it statically stable at that position? And the answer is about 79 pounds per square foot. Neither of those values is the residual strength. If the strength was 1281, it would move an inch and stop. That didn't happen, so the strength was lower than that. And at the bottom, as we discussed, you have to put the brakes on and bring it back to rest. The strength's going to be higher than 79. In fact, it has to be somewhere between those two values, which sort of defines them as bookends. The actual strength could perhaps be estimated by taking the yield value and the residual geometry value and dividing by 2. That would put you somewhere in the middle. And that would be a better estimate than many investigators have made, but you can do better than that. You could take that average or middle value and multiply it by xi. And xi would be a function of distance traveled. If it only moved an inch, xi would be a big number. It would be close to the yield value. If it went a long way and spread itself out like paint across the valley, less than an inch thick, then xi would be almost 0. So xi goes from big to small with travel distance. And we use normalized travel distance, how far the centroid travels versus the height of the slope from toe to heel of the scarp. And if you do that, something interesting happens. These are the back analyses of the 11 class 1 or best case histories done by the incremental inertia, the Pixar animation method. And in those methods, of course, we can track the centroid and we know the travel distance. And so what we've plotted is xi, that's scaling factor, as a function of travel path ratio. How far the centroid traveled divided by the height of the slope. And it fits a pattern. The one down here and one more up there with a dashed line, those are 2 slides where we know the first piece came off first, and then the second piece, and then the rest of it followed, and we have an adjustment factor for those. Then we do the other case histories. There are 31 in all. 9 of them, 9.5 of them, are also amenable to this method. 6 of them are not. 4 of those slid off into bodies of water. One of them was the Baltic Sea, and we weren't going to chase it, but we have bathymetry and estimates of where it landed and what the geometry was, but they're not sufficiently reliable to warrant this method. But if you add the secondary case histories, which we approach by other methods, to this same figure, the pattern continues. And what you have here is a mechanistically simple model which will allow you to make a simple estimate of post-liquefaction residual strength without having to do the Pixar animation. You can calculate SR yield, the before. You can calculate SR fully residual geometry, or the after. Those are trivial calculations. Divide by 2, and frankly, you can look at run out, or you can multiply by about 0.75 and be right in the ballpark. You can beat most of the back analyses that have been done. And of course, if we know the travel ratio, which we do, you can do better than that. But you can also now check everybody else's analyses. That's a terrifying thought if you're some of the other people. Now we know when they're wrong. The last method is a displacement-informed estimate. And this is useful also for back analyses, but it's also useful if you're doing a nonlinear seismic deformation analyses with FLAC or similar. So we'll spend a minute on this. These are calculated factors of safety. The one across the bottom is SR yield, the initial factor of safety. And the other one is the factor of safety at the end of the analysis. These are for the 11 case histories that are class 1, so we know the actual number. So we don't assume that it was 1. We know it was less than that, and we know how much less than that it was. And then when it came to rest, we also know how safe it was. The first thing you'll notice is that every case history had a factor of safety of less than 1, as you would expect, because if it was 1 or greater, it wouldn't be a case history. It wouldn't have moved. The more interesting number is up the other axis. That's the final resting factor of safety, and as you can see, it's not close to 1. An awful lot of people have done nonlinear seismic deformation analyses with FLAC or finite element codes, and they get a deformed geometry, and then they do a static analysis of that deformed geometry, and they expect to see a factor of safety about 1.1 or 1.2. Notice that those numbers vary between about 1.2 to about 2.8. So if you came to rest and calculated a factor of safety 1.2, you weren't finished. You have mesh lock, and you haven't resolved it properly. And you have massively underestimated the deformations of your ongoing flow slide. But you can invert this and make it a predictive tool for back analysis of case histories as well. Okay, so those are 3 methods we used. I want to look next then at 2 other methods. Quick out of the gate were Stark and Olsen, and they did a magnificent job. Joe Weber spent forever, and his wife will never forgive me. I assume Dr. Olsen has a wife somewhere. He's a nice guy. He should have a wife somewhere. And I assume she hasn't forgiven him either. He did a lot of work. And he meticulously documented his work, and as a result, our work was possible. Olsen used a principle developed by Davis, Poulos, and Castro. You can be wrong about the steady state method and still have good insight on mechanics. And they knew that you would basically start at rest, you'd accelerate and decelerate as we looked at with the Pixar animation. And they said, we could do that. We could create a curvilinear path which the centroid of the mass would follow, and it would have a slope, and the slope would define the downslope driving stress, and we could put all the mass, the centroid, at that location and track it down to its final resting position. All you have to do is vary the strength, and you'd have an answer. And you'd accumulate velocity and dissipate it. You'd have acceleration that went from positive downslope to negative to come back to rest. Then you'd have a cumulative displacement. And you could iterate that till you got the right deformation. And they did that for 10 Class 1 case histories, and they got good answers for 9 of them. This is the lower Sanfran Dam, which we're using as our case history today. That's their starting position, that's the curvilinear path they chose, and their finishing position. And from that analysis, which was pretty simple to do, they calculated a residual strength, which wasn't so bad. The one they didn't get right was a Japanese case that was the Shibeka-Cho embankment. The Shibeka-Cho embankment was one of those cases where the nose came off first, and then the rest followed later. They didn't come apart traveling as a group. The nose went, and then the second piece, and then the whole thing went. And they couldn't analyze that by their method because they only had one centroid and one mass. So Dr. Olsen, being from the Corps of Engineers, wanted to be sure if he was wrong, he'd be conservative. And that was a theme in his work, and that's why his resulting relationship was conservative, but still very useful to us. He tracked just the first wedge. And because he tracked only the first wedge, he had smaller masses, and his strength was too small for this case history. So we got 9 good results and 1 not so good. But 9 was better than anybody else had at that point in time, so it was a huge step forward. So we back analyzed 10 cases. He got 9 good answers. Then he analyzed 22 not quite as good cases. We call them secondary cases, or second tier. And for those cases, he analyzed the before and the after. He meticulously documented his failure surfaces and his assumptions, and he documented his befores and afters. And then armed with all that, what he did next was the correct thing at a moral level. He used the after as his estimate of strength. And as we discussed, that number is too low by a factor of about 1.2 to 2.8, on average, factor of 2. So his post-liquefaction strengths for secondary cases, on average, were about half as big as they should have been. And that was a conservative error, and there's nothing wrong with using his procedure. It's just conservative. He also did an admirable job of documenting this, including giving us all we need to evaluate the accuracy of his calculations, the reasonableness of his assumptions, and therefore to make use of his befores and his afters, which is huge because you need someone to compare with. We did the same process. He did a before and after for each case. He didn't have his I value. He just used the after, and his level of over-conservatism is probably on the order of 1.2 to 3.4 or so, on average, about a factor of 2. The final method is the zero inertial force, or ZIF method. This was used by Kramer and Wang. This one is clever. I like this one, as you might expect. Steve's a clever guy. They looked at the same mechanics and said you begin with positive, unbalanced downslope force, and you end up with inertia. Having brought it back to rest, you accumulate velocity and dissipate it. Acceleration reverses as you travel. But there's a moment in the middle where you go from accelerating to decelerating. And in that moment, you're not accelerating or decelerating. And therefore, there is no inertial shear stress transfer between the mass and the foundation soils. If you know the geometry at that moment, you can use a simple static analysis, and you can directly calculate the residual strength. So they did that. This is a case history, one of their cases. The top figure shows the before, the bottom figure shows the after, and they tracked different points as they transitioned, and they tried to infer from the beginning to the end the position halfway deformed. And then at that moment you take a photo and you analyze that. This is one of my favorite written paragraphs of geotechnical stuff. I used to be able to quote it better, but what Steve wrote was, you know the beginning geometry, you know the end geometry. You have a knowledge of soil mechanics, geology, aesthetics, and art. And you creatively play with this until it looks about right. And that's about the size of it. And they got 10 good answers for all 10 cases. Their answers were pretty good ones. So that was huge because now we have 2 sets of comparisons for the 10 primary case histories. They back analyzed their 10 class 1 cases with the ZIF method. They got 9.5 good results. They got a better result for that one where the nose came off because they took it halfway through failing and got more of the momentum and inertia out of the bigger mass. So their answer was pretty good for that case. It wasn't perfect, but the other 9 were really good. Then they had 21 secondary cases, and this was where they made 2 sets of errors. In the secondary cases, Dr. Wang took other people's analyses, some of them undocumented, and he took 2 kinds of analyses. Some were back calculations of S sub R, and some were back calculations of S sub R over P, because there's 2 crowds. When he averaged them, he didn't vet them very carefully, so sometimes he used multiple copies of the same analysis because it had been reported slightly differently or somebody rounded it. And he also didn't require that the cases be well documented. Some of the numbers just aren't very good numbers. And he did something else. When he had his average of S sub R and his average of SR over P, he needed P. And what would you do? You have SR and you have SR over P. You divide one by the other, and you get P. But the analyses were incompatible. The kind of people who did SR were like me. They were old, fuddy-duddies, with dirt under their fingernails. And the kind of people who did SR over P were the critical state people. Bean and Jeffries, people like that, who love that critical state stuff and don't believe in Voidere distribution, even to this very day. And so they analyzed very differently. Some of them wanted one kind of answer, some of them wanted other kinds of answers because they're trying to prove that their prediction was going to work. So it's a hodgepodge. We'll take an example. This is the Nurlurk berm slide into the cold North Sea, and Dr. Wang had 4 values for that. One from Sladen et al., who was the original investigator, one from Jeffries et al., that's Bean and Jeffries' team, one from Stark and Mesri, and one from Olsen. But if you look at it closely, and if you've read all those references, turns out that Bean and Jeffries' value was adopted by Stark and Mesri, who simply rounded it to 300, so that one's redundant. And then you find that Jeffries and all didn't document it. They don't show you a cross-section. They don't tell you what their assumptions were. And they like high numbers because they're trying to make critical state work. And so we don't like that value. We think it's wrong. Plus, of course, we did this case in our study. In our study, we got about 68 pounds per square foot. So we think you've got a 42, a 54, and a 68, and maybe the answer's somewhere in the mid-50s, maybe the upper 50s, which is very different from the 176. Now, sometimes they went higher, sometimes they went lower. There is a small overall bias, but this was almost a neutral thing in terms of bias. What they got was more variance or uncertainty as they did their probabilistic regression when they were all done. So this affects mainly their variance. But the other problem they had was they took the SRs and the SR over Ps and divided one by the other, and since they were incompatible, they didn't get good answers. So this is a table of all the cases, and the first column here shows Olsen and Stark's representative value of vertical initial effective stress average over the failure plane. The second one shows our estimate of that value. And the third column shows the ratio between those first two columns. And what you'll see is those answers are usually pretty close to each other. Sometimes they chose a slightly deeper failure plane, sometimes we chose a slightly deeper one, but by and large, we're in the same neighborhoods. We all know how to calculate effective vertical stress, and we got pretty similar answers. The two at the bottom down there, which are the Nerlerk embankments, we had a significantly different view than them as to what the failure surface was. But on average, we're about 10% apart. That's pretty good mutual support. So we took that to be the right answer. That creates the next column, column 3. You add column 1 and 2, divide by 2, and take that as the average answer. And then you look at Kramer and Wang's values and take the ratio of our average, Olsen and us, and you get numbers that aren't necessarily close to 1. And that's because the SR over P and P were incompatible in many cases, and so they got some answers which were just simply not correct. One of the good examples is here. This is the tailings dam failure. And the entire embankment isn't thick enough to get you anywhere near that value. So a priori, it's a wrong answer. On average, they're about 60% high on their effective stresses, and this does bias their overall correlation. The good news is it biases it conservatively. It stretches the vertical effective stress axis out, and it lowers their strengths by the stretching. Steve's on sabbatical leave this semester. He's in Christchurch, which is a great place to be, even if you're not on sabbatical. And one of the things he's going to do is he's going to tackle and fix this. So he'll have a new correlation sometime in the next 6 months or so if we're lucky. And his correlation will probably move closer to ours. His variance will come down, and he'll unstretch his axis and get better vertically effective stresses. That's a simple calculation to make. Okay, these are the case histories analyzed that matter. And for 3 sets of studies. 4 sets of studies. Seed and Harder, Stark and Olsen, Wang and Kramer, and us. In the Stark and Olsen category, the SR values for 10 of the cases are back analyzed directly by their kinetic method. For the secondary cases, they're shown in square brackets. In the square brackets, we didn't use their answers. They took the after value, SR fully residual. We took their before and their after, added them up, divided by 2, meaning we took the average, and we multiplied by 0.8, and those are the values shown. If you track them across the page, there's at least 2 answers that agree very nicely with us, except for the last 2 cases, which are new ones that we added. And agreement among all 3 sets are pretty good. The vertical effective stresses of Wang are not very good for secondary cases. They're kind of randomly high and low, but more often high because of the SR divided by SR over P. But by and large, we take this to be mutual confirmation by 4 different research teams, taking very different sets of views and getting similar answers for essentially the case histories that matter. So we took that as a positive, and that's the beginning of perhaps some consensus. And then you regress that. If you're me, you don't regress that. I did a minor in probability and reliability, but I am not qualified to do this. This is the work of Rob Moss, Professor Rob Moss of Cal Poly. There are 6 bona fide liquefaction experts who can also do high-end Bayesian regressions. Rob is at least one of them. He might be two. He has a book on the topic. Does this pretty well. The one axis to the right is N160 CS. The axis to the left is vertical effective stress in atmospheres, sigma prime VI, the initial effective vertical stress. And the vertical axis is the post-liquefaction residual strength S sub R. The dots are the case histories. The figure at the bottom is the residual. That's how far each case history is from the mean correlation if you made that into a flat sheet. Some of them are high, some of them are low. The thing to notice is the scale of the bottom figure, the vertical scale, is twice as big. The fit is very good. The bias is fully random. There's no systematic bias. You get highs and lows in all possible directions. It's a remarkable predictive regression. And that's why Rob Moss is who he is. Plus, he fishes better than I do. He grew up in Bozeman. I live there now, and we traded. He's in California, but he's a really good fly fisherman. If you ever want to fly fish, take Rob with you. But he's really good at Bayesian regressions. And you can take that surface, and you can slice it in different directions. You can do it as SR or as SR over P, but in either case, it has to be SR as a function of both N160 CS and sigma prime VI. So we have two sets of figures. The top figure is SR versus N160 CS, and then you have lines labeled by different initial vertical effective stresses. The bottom figure is the same. It's SR over P, but each line is again labeled by its initial vertical effective stress, and they flip. And what you have is a relationship that looks a lot like Kramer's relationship. At the top, has the same kind of shape and form, and that's not surprising. That's the physics of the problem. That's what you would expect it to look like. Plotted also are the data points, and they're sized by their vertically effective stress, give you a sense of how the correlation fits for the various cases, but also where the data are. And then you can carry that forward and ask yourself as an engineer, what does that mean? So this is an important figure. This is that same relationship with the same data points plotted, but we've changed the axes and scale. We're doing it as SU over P. It would work equally well the other way. And what we're showing you is what the residual strength would look like as a function of N160 CS for different overburden stresses. And you come up into a gray zone. And the gray zone is called drained friction cutoff. The bottom of the grain zone is whatever your vertical effective stress is times tangent of 30 degrees, a rough estimate of a residual friction angle for a cohesionless soil. The top is that. It's tangent of 30 degrees times vertical effective stress. The bottom line is 0.5 times tangent of 30 degrees, which would represent the back heel scarp. The other one would represent the flat bottom portion of the slide. Once you're up in that box, your post-liquefaction residual strength is more or less the neighborhood of drain behavior. And for those of you who've done liquefaction stuff, once you're in the neighborhood of drain behavior, your troubles are over. You've got pretty good strength. You're not going to have a flow failure. So getting up into that box is the point at which you get out of the woods. How soon you get out of the woods in terms of N160 CS is a function of your overburden stress. At 0.1 atmospheres, I would suggest we don't care. I haven't found a problem yet where I'd worry about what happens at 0.1 atmospheres vertical effective stress. Maybe half an atmosphere to 2 atmospheres for shallow foundations. For big dams, 2 to 8, sometimes 10 or 11. So the values out to the side here are the engineering values of interest. And what happens is that blow count in the upper teens into the lower mid-20s is where post-liquefaction residual strength puts you in a neighborhood where if you liquefy, it is not a disaster. You get some deformation, but you will not have big movements. You'll have small movements. You might get some distress to your structure, but you're not going to tip a building over. You're not going to have a flow slide go 143 feet back into the reservoir or a massive loss of the crest of your dam. And that's the good news. These are Professor Kramer's values. This is his regression, but we call this Kramer and Wang because Wang did the background work for the data points. And it's a similar figure. Same pattern. He's got SR. In this case, you can do it as SR over P. He's got both figures. And you can plot them versus N160 or N160 CS. He chose N160 So in a minute, we're going to have to modify that for him to compare with ours. These are the standard deviations of those two correlations. His regressed failure surface looks a lot like ours. And what happens is uncertainty goes up as you get higher P, which is the right-hand bottom axis, and higher N160CS, which is the left axis. Kramer's uncertainty is a lot harder than a lot higher than ours, and that's because he had those SR and SR over P values, and he was averaging them. That gave him a lot of variance. It wasn't a systematic bias, but he had a lot more variability. He'll fix that. His variance will come down, I think, in his second iteration. That'll be good too. Here's a comparison between his values and our values plotted as SR, which is how many engineers prefer to use it. It speaks for itself. The problem is his values are based on N160, ours are based on N160CS. We can approximately fix that by varying his equation a bit. What we do is we add about 1.5 blows for a fines correction at the left-hand axis and about 2.5 at 16 blows per foot. And we can stretch his values out a bit. And this is almost a direct comparison. This is our N160CS, and it's approximately his average N160CS, the same situation. And what you'll see is that on the left, at very small n values, his answer is a little higher than ours. On the right-hand side, his values are dropping below ours because ours are curving up more quickly. That was kind of an expected result. When he did his three-dimensional regression, he realized he'd probably overestimated with his equation the values at very low stress, and so he picked them up a bit based on analysis of some shallow flow slides, and that tilted his relationship, and it tilted down. He may also fix that. He may leave it. It's not a fatal problem. It just makes him conservative for bigger projects, deep foundations, and big dams. But it's the beginning of consensus. Never before have two groups come so close to agreeing, not just the form and shape, but to the actual values. There's nothing wrong with using Kramer and Wang's values. They are probably conservative. Okay, then we're going to compare with Olsen and Stark. We talked about it earlier. Their problem was their secondary cases, which were biased low by factors of about 1.2 to 3.4. And so they have apples and oranges in their plot. This is their relationship. They've got 10 good values and 20 values that are too conservative. And when you have apples and oranges, you have a lot of scatter, and it's harder to see a pattern. The proposed relationship is not a bad one. It's conservative. How conservative is it? Well, now we can answer that question by plotting it on our figure of SR over P, and the answer is that's how conservative it is, depending on your N160CS value and your vertical initial effective stress, sigma prime VI. It's certainly safe to use for most projects. It's also very similar to the Idris and Boulanger SR over P relationship, except that theirs curls up more to the right, and we'll look at that in a minute. Seed and Harder had this line here. Most people would draw a line down the middle, usually a dashed line. It's often red. If you transpose that onto the new relationship, turns out Seed and Harder's values aren't so bad at a vertical effective stress of about 2 atmospheres, which is sort of the median of the range. If you have higher overburden stresses, this is conservative. If you have lower overburden stresses, this is unconservative. It's too high. And that's not a surprise. All the relationships which only use N160CS and not also as a function of sigma V prime are going to have problems in one direction or the other. If it's SR, it's one way around. If it's SR over P, it's the other. Idris and Boulanger have two relationships. One is just SR. The other one's SR over P. This is their SR relationship. They made the same mistake my father made because they used his data point. Point A there, that's the lower Sanfran Dam, plotted too high because it's based on the initial or before geometry. It belongs down with points B and C, which are calculated for a condition between before and after. But having said that, their curve is interesting, partly because it doesn't follow the data. I kind of enjoyed that. There's good engineering judgment here. And you can plot it over here, and it's about the right kind of curve for 1 atmosphere. And that means that for a shallow foundation and a 1-story home, it's a pretty good answer, and it's conservative for all other purposes. So if you've used Idris and Boulanger's SR, not SR over P relationship, you have probably been conservative for big projects. You probably gave away a fair bit of strength. They also have an SR over P relationship. Again, Sanfran Dam needs to be brought down. A lot of people think this dot anchors this curve here. It does not. This curve here is based on Japanese testing data from Tokyo University. It's a large data set, but it's laboratory data, and it's done by people who don't believe in Fourier distribution. And so this is a curve for where no Fourier distribution happens. I always turn to the class at this point and say there are no cases where Fourier distribution doesn't happen. Dr. Idris has argued on some projects that this would be applicable perhaps if you had vertical drains draining your material, and that's not my view. If you have vertical drains, what you're getting is extensive and very rapid Fourier distribution. In fact, you're spewing water out and changing your volume. That's also not what this does. These are undrained tests of constant volume. So the vertical line there doesn't exist as I know it. The other line, though, is interesting, and it's not so bad. It's a lot like Stark and Olsen, except that it bends up a bit more to the right. It's the bottom solid line. The no Fourier distribution line cuts up more sharply, and I would not recommend using that unless you're sure you have drain conditions, in which case you should just use drain conditions, because it's a better value. So our objectives were to do all of these things. We want to do a better job of picking and vetting case histories. We wanted better methods for back analysis. We wanted to have more than one. We wanted to use as many as possible on the class 1 cases, so we did 14 class 1 cases, not just the 9 or 10 of other people. Then we wanted to use full diligence for the secondary cases. We wanted methods for cross-checks between our analyses of different methods and cross-checks between mechanics-based checks and cross-checks between everybody else's analyses. Didn't mean we wanted to match everybody's analyses, but if theirs was different than ours, we wanted to know why, and we wanted to be sure we liked our answer after we figured out why. Then we want to do a higher order Bayesian probabilistic regression, and at each step, compare and compare and compare. This is the regression equation. In case you guys get the slide sets, sometimes that happens after these talks. This is the reference for it. It's a draft final report to the U.S. Nuclear Regulatory Commission of August 2015. We haven't finalized it yet, partly because we're waiting to work with Steve and resolve his stuff, and probably because I got buried in a second research project right after we finished this, and I am officially retired, and so my wife only cuts me so much slack. This is the regress relationship, and it is objectively a better deal. These are higher strengths than you've probably been using, unless you're a Bean and Jeffries fan and you've been doing lab testing, in which case this won't please you at all. And these are the values. So I want to take a second then and change directions very briefly and tell you there's something bad coming down the pipe. This is that last research project, and this is now Dr. Khalid Chowdhury. He filed his dissertation in January at UC Berkeley. He works in the Corps of Engineers Seismic Dams Group. And what he spent the last 4 years doing, and his wife has not yet forgiven me, is nonlinear seismic deformation analyses in FLAC of both the upper and lower Sanfran Dam case histories, which are very well defined, using 4 different analytical models, 3 different triggering relationships, and 3 post-liquefaction residual strength relationships. And it's been very interesting. One of the findings is these analyses can be surprisingly accurate. We were almost blown away by some of the accuracies achieved. So I'll look at that very quickly. We reworked all the seismology. My father developed the motions people have been using for the last several decades. He did it wrong. What he did made perfectly good sense in 1971, which was the dawn of time, but there were 3 large velocity pulses which were considered weird, and it was a bigger PGA than anybody had ever seen before. So we trimmed the velocity pulses and then scaled the record down. Both of those were wrong. The dams themselves occur here and here. This is the surface fault rupture. These are fault planes dipping down in that direction away from you. And this is a second plane over here dipping down away from you. And so what you are, and the epicenter was here, it came up the deeper fault and then transferred to the shallower fault. And upper and lower Sanfran dams are on the upthrown block near the corner of a very near field fault, passes less than a mile from the lower Sanfran Dam. That's as tough a condition as you can try and develop ground motions for. So we took 4 different approaches. One of them was to use the Skek Center's simulation program, which is built specifically to answer this question. One of them was to use multiple NGA West attenuation relationships and a recently developed suite of ways of averaging those results for a corner location, which is not ideal. And we looked at instrumentation available, including a historic seismoscope record. 3 different triggering relationships, 4 analytical models, and 3 residual strengths. But the triggering relationships are the one I want to point out tonight because it's going to make the residual strength more important. The top figure there are the 3 triggering relationships used. As you would expect, we used Yount et al. 2001, Boulanger and Idris 2014, the right-hand figure, and Chetan has a new relationship. He's revised his. Idris and Boulanger had some issues with it. He's addressed those. He made some changes, and some he didn't, because some of the case histories they challenged were his own case histories from our teams. And our policy is if people on site are experts and know what they're doing, we take their word for it, even if it's us. If you look at the top figures, they are unique. This is the bad news. Those 3 figures, for the first time, are plotted side by side at the same scale. It's never happened before. Vertical and horizontal axes are the same scale. And so right away, you can begin to see differences. For instance, the dots might be higher or they might be lower as a function of how the back analyses were done. And then the fitting of the dots by the curves might be higher or lower as well. And that changes the answers. So there's 3 levels of conservatism in the upper 3 figure. Chetan is the least conservative relationship. His dots plot lower because he analyzed stresses using a nonlinear site response code. Idris and Boulanger probably used non-representative RSD curves because they had 5 sand sites and 1 layered site, which they made stiffer than the sand sites. And so they had overly stiff RSD curves. Their dots are high as a result. Yount et al. Is actually Seed, Toki, Matsu, Harder, and Chung, 1984, with a little bit of a dashed line in the bottom left corner, applied by the 20 experts who are now called Yount et al. I'm one of those guys. The dash curve is not a bad one. It's an intermediate level of conservatism between Boulanger and Chetan. So until that gets more fully resolved, that's how it is. You got 3 levels of conservatism. You also have 3 levels of conservatism on K sigma, which is a big deal as you get to depth. The figure at the bottom is the existing K sigma database. The open circles are cases that were gathered together by Montgomery as part of his dissertation work at Davis, but they come from multiple teams. There's some extra dots on there that are data points Montgomery didn't have. We added them. And then you've got the black line and the black dashed line. Those are the recommended K sigma relationships recommended by Yount et al. And they're also recommended by Chetan et al. For use with their triggering relationship. Boulanger and Idris like the 2 blue lines at the top. As you get to high vertical effective stresses, that makes a big difference. So it's a big deal for dams. And the different conservatisms up top get multiplied by the different conservatisms down at the bottom, so they compound themselves multiplicatively. And I should tell you that the red lines there are Chetan's regressions of K sigma, and they are unique. He's the only person who's managed to regress K sigma from the same field performance liquefaction case histories that were used to develop the correlations for triggering. I mentioned earlier that Rob Moss is an absolute genius, and he has a book on Bayesian regression for liquefaction applications, but for other purposes as well. Rob would argue that Chetan's better at it than he is. He is a genius. No one's done this before, and no one's tried to match it yet either. It's a huge regression with an enormous data set, and I think 11 variables. It's really hard to do in a probabilistic framework. You don't have to use the red lines, but they have a significant advantage. All the other lines are based on cyclic triaxial and cyclic simple shear laboratory testing, but there's one directional simple shear, and it's pumping up and down. Earthquakes don't do either. They shake in all possible directions, and simple shear is the dominant mode. The field data shakes in all directions, and it has a perfect boundary condition. It's got the field as a boundary condition. So the red lines might be sort of the right answer. Once his data set, his K sigma values are only valid from about 0.3 of an atmosphere to about 1.8 atmospheres, because the shallow range is where the data set is for triggering. If it triggers at great depth, We don't know. And if at great depth it doesn't trigger, we don't know that either. So all the triggering case histories tend to be shallow. You could, in theory, extrapolate at great depth with any relationship you like, but it would seem bold to extrapolate with a relationship that doesn't match the field regress values down to about 1.8 atmospheres. And I point that out tonight because we're essentially unleashing higher SR values, which is good news. But I want to caution you that triggering is probably going to get worse because it's entirely possible that the Idrison-Boulanger triggering relationship is unconservative, and especially at depth. And so triggering might get more severe. And it might bite hardest in places where you have long duration subduction events. You may need SR values. These are the back analyses, almost done, by the core of the lower Sanfran Dam. We're only going to look at one of them. This is analysis done with the PM4 sand model done by Chetan's triggering, Youd's K sigma at the end of shaking. And you get pore pressure and the lower hydraulic fill zones upstream and downstream side. In the middle you have strain contours. You've got two incipient failures, one to the upstream side and one to the downstream side, and the crest is settled about 6.8 feet at the end of shaking. But if you continue the analysis forward in time, the upstream side is going to progress and the downstream side is going to remain stable and just sit there and grin at you. And so what happens is you get an upstream side flow failure as shown here. The accuracy to us was staggering. The heel scarp elevation, which is what defined the freeboard at the end of the event, is elevation of 1,114.8 feet. And we put the 0.8 on because the field measurement was 1,114. We didn't want you to think that we nailed it exactly. Not only that, but the heel scarp geometry is very good, agrees closely with the field observations. What we haven't got is the run out. We carried this one out about 39 feet, as I recall, and so this is a message for those of you who run FLAC for nonlinear seismic deformations. You can't stop at the end of shaking, and you can't stop anywhere until it stops moving. But you can't carry it forward either, because what happens is you have to remesh and remesh. It becomes very tedious. You can let FLAC do it for you, but that's a really ugly remeshing, and it gives you less and less accuracy more quickly. But even if you do it by hand and you're careful, you're losing accuracy because you can't stretch the elements infinitely and get a good answer. So one of the outcomes of Dr. Chowdhury's work is a recommended criteria for when you stop. And there are two options. One is you stop when it becomes stable, if that happens at a reasonably small deformation. The other option is you stop when remeshing is tedious and you can tell what the answer is. You haven't got to remesh to depth. In this case, the crest is dropped below the lip. It's obviously going to travel further. In this case, as we know, it goes 140 feet back into the reservoir. But that bottom figure is your engineering answer. As long as you understand that it's still moving, you know everything you need to know as an engineer. Okay, this is the other analysis. This is PM4 sand model again. We used 4 different models, but I'm using the same model here. There's nothing wrong with PM4 sand. That last analysis with PM4 sand nailed it. So did analyses with the Roth model, so did analyses with UBC sand, and so did analyses with Wang 2D, which is another Defalius bounding surface plasticity model. This is the conditions at the end of shaking and the analysis with Boulanger and Idris triggering and Idris and Boulanger residual strength. And what you have is zones in hydraulic fill layers 2 and 4 on the upstream side where you haven't generated enough pore pressure to liquefy. The criteria we use for that is a seismic cyclic pore pressure ratio of RU seismic greater than 0.7 or shear strains of greater than 10%. Not two directional, but one directional because you're moving down the slope under K alpha conditions. It met neither criteria. And so you've got two strong spots buttressing the upstream side of the core. You've still got two incipient failures. The downstream one is not going to fail, but unfortunately, because of the buttressing effect, neither is the upstream one. So at the end of analysis, you've got 7 feet of crest loss, and you are stable. There is no upstream flow failure in the lower San Fernando Dam. That's not good. It's daunting. And so triggering will probably get worse, and post-liquefaction residual strengths are probably going to matter. Thank you.
So I think we have some time for some questions here. Are you willing to take some questions?
Sure. The question is, how do we differentiate and deal with the fact that some of our cases are static failures and some are seismic failures? And the answer, of course, is very carefully, but there's more to it than that. The seismic cases probably had more cyclic voided distribution before they began to move. But when they began to move, they became large deformation cases, and the static ones did also. So there's strong similarities at large deformations, and there's some differences at the initial inception conditions. We don't have an answer for that. The best we can do is use the data we have. Our notion is that failing cases tended to be loosish, and there probably was voided distribution occurring in the static cases as they were occurring. But we can't prove that, and we're not sure. Pixar animation, yeah. If you were 14, you'd know all about that. It's an incremental analysis where we track driving forces downslope constantly as it deforms, and we're resisting forces upslope constantly as it deforms, and they're changing. For instance, we strain soften the clay core for a while. So it's essentially a bookkeeping method, and you can carry it forward in steps or increments. There's no shaking forces because it's just under gravity loading. And I should point out that when we do the back analyses of the lower Sanfran and our dam, the crest tends to go down 3 to 6 feet during shaking if you transition to residual strength during shaking, but there's not much velocity. The main failure occurs clearly after the earthquake is over, so it's almost a static deformation having been triggered by cyclic pore pressure generation, which is common. Not all the cases do that, but it's common.
So how do you deal with the water film issue? I mean, you've got the block out, and then you've got the size, so you've got a series of loose soil and water film, and that's what you let out of the residual strength. Different sites will have different kinds of layering.
I love you guys. There's 2 pieces of that. There's a second kind of water film too. The water film issue we're just handling statistically. The layering occurs at different scales. We can't measure them, so we're treating the whole material as a mass. Layering scales will differentiate. If you knew you had bigger layers, you might penalize your SR values. But there's a second water film issue that we'll also have to deal with. Lower Sanfran Dam is a good example. As the material moves back into the reservoir, it's moving at a pretty fair clip. And so it's capturing a film of water as it engulfs it, and it's plowing through soft reservoir sediments, which have almost no residual strength. It's almost like sliding on grease. And those 2 phenomena are clearly occurring, and they're not usually handled within geotechnical analyses for a forward analysis of a project. They do get handled routinely in the offshore industry, but there's some big approximations that go into that. We use some approximations of that. So there's 2 kinds of water film going on. They're both challenging. We haven't got that resolved yet, which is the value of having more cases. Speaking of which, I have some news also. Dr. Moss isn't only good at Bayesian regressions, he's also just finished processing a tailings failure case history from Chile, and we have a new class 1 case history data point. He hasn't shown it to me yet. I've asked him not to. But he says, we're going to like it. It plots very nicely on the relationship. We won't have to redo it. Great.
Very good.
Thank you very much.
Thank you. My name is Greg Fisher. I'm the chairman of the board of Shannon and Wilson. I just have a short closing announcement. First of all, when we plan this event every year, we try to do three things. We try to find a speaker who's world-renowned, and we succeeded today. Secondly, we try to find a speaker who will speak to a topic that's of interest to the geotechnical engineering community, and based on the show here, in fact, I was counting, it's over 100 people. It's a great turnout, so I know we succeeded on that. The third one's the hardest one. The third one is to try to find a speaker with relationship to Stan Wilson. And I know you were probably too young to know Stan, but Stan and his father, Harry, were very good friends and colleagues, and sadly, they passed away within years of each other. But we have some great photos even of Stan and Harry together, so we got that link there, and it's great to see Ray here representing his father as well as himself. And part of this is that we have many people to thank along the way as well for putting this together, and I'd be remiss without mentioning our friends at the University of Washington and their participation, and as well as the Shannon and Wilson individuals, which I can't name them all, but Mike Harney is essentially our project manager on this, and so Mike does a great job of arranging this every year. In appreciation for your speech here today, I have a plaque and an honorarium for you, and I thank you very much for your presentation. It's an honor.
Thank you very much.
We have some food and hopefully some fellowship down the hall here, so if you go out the door, take a right and a quick left, you go all the way to the end there, and you can go down there and hopefully visit with some of your colleagues. In closing, I want to thank everybody for coming here today. I want to thank Dr. Seed again. I want to thank you for being an attentive audience, but most of all, I want to really thank you for helping us honor and celebrate the legacy of Stanley D. Wilson. Have a great evening.